A number of electronically controlled devices and systems, such as the EFI engine, the electronically controlled transmission, cruise control, the digital meter, and the sunroof are used in Toyota vehicles. Of these devices and systems, that which is used to electronically control the engine is called the Toyota Computer Controlled System, or TCCS. The TCCS consists of the sensors which detect the running conditions of the engine, the electronic control unit, or ECU, which based upon signals from the sensors and on data stored in its memory determines how the engine shall be controlled, and the actuators, which actually control the functioning of the engine. The TCCS is used with various engine models, and although the TCCS construction and operation for a particular engine may differ from that for other engines, we would like you to remember that all TCCSs operate in basically the same way. The TCCS has a number of functions, such as electronic fuel injection, or EFI, electronic spark advance, or ESA, the idle speed control system, or ISC, a special air intake control device called the Toyota Variable Induction System, or TVIS, a diagnostic function, a fail-safe function, and a backup function. In this video presentation, we will focus on the EFI, or electronic fuel injection, of the 4AGE engine, which ensures that an optimum amount of fuel is injected into the intake manifolds to best meet the running conditions of the engine. We will study about other functions of the TCCS in Volume 2 of this video presentation. Now, let's begin our discussion, starting with the major electronic components that belong to the EFI of the 4AGE engine. First, let's talk about the sensors. The vacuum sensor detects the intake manifold pressure. The throttle position sensor has two functions. It detects whether or not the throttle is fully closed, and it detects the throttle opening angle. A pair of sensors is built into the distributor. One is the NE pickup sensor, which detects the crankshaft angle and the engine speed. The other is the G pickup sensor, which detects the standard crankshaft angle, which is used by the ECU in determining the output timing of the injection signals. The water temperature sensor detects the temperature of the engine coolant. The intake air temperature sensor detects the temperature of the intake air. In addition, when the engine is cranking, the ST terminal of the ignition switch informs the ECU of this. Each sensor sends a signal to the ECU in the form of either a voltage or a pulse signal. The ECU contains in its memory data on optimum values, and it compares these incoming signals with the stored data, then calculates the optimum fuel injection duration and injection timing. The ECU also constantly monitors the battery voltage. Based on the results of its calculations, the ECU sends signals to the injectors, each of which injects fuel into the intake manifold. Finally, there is the cold start injector, which is one of the actuators, but which is not activated by signals from the ECU. Instead, it is activated directly by signals from the ST terminal of the ignition switch and from the start injector time switch. Now, let's look at the basic system diagram again and see how the TCCS controls EFI. EFI consists of three parts: the fuel system, the air induction system, and the electronic control system. First, let's look at the fuel system. Fuel is pumped out of the fuel tank and pressurized by the electric fuel pump, then is sent to the injectors and the cold start injector. The fuel pressure is controlled by the pressure regulator. The fuel pump itself is controlled as follows. When the engine is cranked, the circuit opening relay is turned on by a signal from the ST terminal of the ignition switch. This causes electric current to flow to the electric pump. When the engine begins cranking, an engine RPM signal is sent from the distributor to the ECU. Once the ECU receives this signal, it maintains the circuit opening relay in the on position while the engine is running, even after the ST terminal of the ignition switch is turned off. This ensures that electric current continues to flow to the electric pump. Let's see how the fuel system looks on an actual vehicle. The fuel, which is fed forward by the electric pump, passes through the fuel filter and the delivery pipe to the injectors and the cold start injector. The pressure regulator maintains the fuel pressure in the injectors at 2.55 kilograms per square centimeter higher than the intake manifold pressure. Every time the injector injects fuel, the fuel pressure fluctuates slightly. These fluctuations in fuel pressure are absorbed by the fuel pulsation damper. Next, we'll discuss the air induction system, the second part of the EFI system. Air is drawn into the air intake chamber, the volume depending upon the throttle valve opening angle and the engine's speed. Then the air is led into the intake manifold of each cylinder where it is mixed with the fuel. The air-fuel mixture is then drawn into the cylinder. While the engine coolant temperature is still low, the air valve automatically opens to allow the intake air to bypass the throttle valve and flow directly into the air intake chamber. This provides a large amount of intake air even when the throttle valve is fully closed, thus allowing the engine to run at a fast idle. Now, let's look at the third part of the EFI system, the electronic control system. The ECU calculates the fuel injection duration that best fits the running conditions of the engine, based on signals from the various sensors and data stored in its memory. It then sends an appropriate injection signal to the injectors. In the 4AGE engine, an injection signal is sent to all injectors simultaneously with each revolution of the crankshaft. As you can see, half of the fuel required by the cylinders for one engine cycle is injected with each revolution of the crankshaft. Watch this demonstration. When electric current flows to the injector valve opens and fuel is injected. Fuel is injected only while voltage is applied to the injector, as you see here. In an actual car, the ECU plays the role of the switch we just saw in the demonstration. Since the fuel pressure is maintained at a constant level in relationship to the intake manifold pressure, the amount of fuel injected into the manifold varies according to the duration of the injection signal sent by the ECU to the injectors. How does the ECU determine the fuel injection duration? Basically, the ECU determines the fuel injection duration based upon the amount of air that is drawn into the cylinders. So, let's see how the ECU detects this. Actually, the amount of intake air is detected in several different ways. In the so-called L-type EFI, the amount of intake air is detected directly by an airflow meter. In the D-type EFI, the ECU detects the amount of intake air indirectly. That is, signals from the vacuum sensor keep it informed of the pressure in the intake manifold, from which it calculates the amount of air being drawn into the cylinders. Since the 4AGE engine that we're now discussing uses the D-type EFI, we need to fully understand the relationship between intake manifold pressure and the amount of intake air, and their relationship to the fuel injection duration. When the throttle valve is fully or almost fully closed, only a small amount of air is drawn into the intake manifold. Therefore, the manifold pressure is very low, as shown by the vacuum gauge. Based on signals from the vacuum sensor, the ECU determines that there is only a small amount of intake air in the cylinder. The ECU, therefore, reduces the fuel injection duration so that only a small amount of fuel will be injected. To make it easier to understand the relationship between the pressure in the intake manifold and the amount of air drawn into the cylinders, let's assume that the speed of the engine is constant. If the throttle valve opens but the engine speed remains constant, for example, when the load on the engine increases, more air will be drawn into the intake manifold, and the manifold pressure will approach atmospheric pressure. Signals from the vacuum sensor inform the ECU that the amount of intake air has increased. The ECU, therefore, increases the fuel injection duration so that more fuel can be injected. However, measuring only the manifold pressure is not enough to be able to determine the amount of intake air precisely. This is because even if the manifold pressure remains constant, the amount of air drawn into the cylinders will change if the engine speed changes. For this reason, in the D-type EFI, the fuel injection duration that the ECU roughly calculated based on the manifold pressure must be corrected by engine RPM signals to allow the ECU to more precisely calculate this duration. After the fuel injection duration has been corrected by engine RPM signals, it is called the basic injection duration. Injecting fuel into the intake manifolds in accordance with the basic fuel injection duration ensures that the air-fuel ratio will be maintained at 15:1, or nearly the theoretical air-fuel ratio. To see how the basic injection duration changes, let's look at an actual injection signal sent by the ECU to the injectors. This is an oscilloscopic image of the waveform of an injection signal. Its length represents the injection duration. This injection signal is for a vehicle traveling at about 40 kilometers per hour or 25 miles per hour on a level road. Now, the vehicle comes to a gentle slope. The driver depresses the accelerator pedal slightly in order to maintain the same vehicle speed. So a signal from the vacuum sensor informs the ECU that the manifold pressure has increased a little. As you see here, the ECU increases the length of the injection duration accordingly. As we mentioned a minute ago, the basic injection duration maintains the air-fuel ratio at nearly the theoretical air-fuel ratio. However, the basic injection duration alone cannot cover the entire range of possible driving conditions. For this reason, the Tccs depends on a variety of other corrective measures to obtain air-fuel ratios that best match the actual driving conditions. We will now simulate some of the more common driving conditions and see how the injection duration is controlled. First, we start the engine. Let's look at the system diagram again. When the engine's speed is still very low, as when the engine is being cranked, the vacuum sensor cannot detect the manifold pressure very accurately. For this reason, the ECU selects, based on the temperature of the coolant, a basic injection duration from the data stored in its memory. Then, the ECU determines an actual injection duration by correcting the basic injection duration based on the intake air temperature in order to maintain an appropriate air-fuel ratio, and on the battery voltage in order to compensate for the operational delay of the injectors. As a result, only the amount of fuel that is necessary during engine cranking is injected by the injectors. These two types of corrections, one based on the intake air temperature and the other on the battery voltage, are carried out not only during engine cranking, but also during normal engine operation. In addition, if the coolant temperature is low when the engine is being cranked, the cold start injector is actuated by a signal from terminal ST of the ignition switch to make a richer air-fuel mixture. The duration of operation of the cold start injector is independently controlled by the start injector time switch. Now, let's see how the injection duration is controlled after the engine has started. When the engine's speed increases to a predetermined RPM, the ECU judges that the engine has started. Once the engine has started, the ECU begins calculating the basic injection duration based on NE signals, that is, engine RPM signals from the distributor, and signals from the vacuum sensor, instead of the coolant temperature signal that it monitored during cranking. However, the ECU still corrects the basic injection duration, mainly on the basis of the coolant temperature. While the coolant temperature is still low, the ECU increases the fuel injection duration in accordance with signals from the water temperature sensor in order to improve drivability. Let's see another injection correction. First, we accelerate the engine. The ECU judges the rate of engine acceleration in two ways. It determines that the engine is accelerating if the throttle valve opens from the fully closed position. In such a case, the throttle position sensor sends signals to the ECU, which corrects the injection duration by increasing it accordingly. The ECU also detects the rate of engine acceleration if the manifold pressure increases sharply. The amount of correction during acceleration also increases if the coolant temperature is low. Now, a heavy load is applied to the engine. When the driver depresses the accelerator pedal more than a certain amount, the throttle position sensor sends a signal to the ECU to inform it that the engine is running under a heavy load. The ECU therefore corrects the fuel injection duration by increasing it accordingly. The car is now coasting. That is, the driver has removed her foot from the accelerator pedal. In such a case, the throttle position sensor sends a signal to the ECU, informing it that the throttle valve has been completely closed. If the engine is running at a speed faster than a predetermined RPM when the accelerator pedal is released, fuel cutoff occurs. That is, the ECU temporarily stops sending injection signals to the injectors. After the engine speed drops to a predetermined RPM, the ECU resumes sending injection signals to the injectors. Even if the engine speed is high, injection is also resumed if the accelerator pedal is again depressed. We have just seen the main EFI functions. This brings us to the end of Part 1, Volume 1 of our video presentation on the Toyota computer-controlled system. In Volume 2 of this video presentation, we will talk about ESA, ISC, TVIS, and the diagnostic, fail-safe, and backup functions.